we've had a look at Newton's first, second and third law, and now we're going to take another step forward in representing diagrams showing force. They're known as free body force diagrams or just free body diagrams. Basically they're just used to show the force on a single object. Not just a force, showing all forces acting on an object. There are a few rules about these diagrams, not so much hard and fast rules, but just common ways of representing certain parts or certain aspects of these diagrams. The first is that the diagram is for one object only. So we're not so much concerned about multiple objects in this case. And it shows the forces acting on them, on that object, using arrows. Second thing is that the only the forces acting on the object. So we're not looking at the forces that the object exerts onto other objects. We're only looking at the forces acting on the object of interest. The next one then is that the force arrows are actually drawn to scale. So this is a scale diagram to show, so we can look at the relationships graphically in terms of the sizes of the forces that are involved. And those force arrows originate at the center of mass of the object. So we're considering the object as basically all the forces are affecting the center of mass. That means we can simplify diagrams quite significantly as well. The last thing is that all the forces are labelled. So to help us make a little bit more sense, we'll look at a few examples, and then in class we'll go through and do a few more problems looking at force body diagrams. So in this scenario, I'll state what the example is in words. I'll draw a rough diagram of what that represents, and then we'll have a free body diagram of the forces acting on that object. So we'll look at three examples here. The first is a free-falling ball. So if you think about that scenario, there's the ground, here's a ball, it would be falling that way, it would be accelerating due to gravity, so it'll have a gravitational acceleration on it, and it will also be moving with some velocity in that direction as well. Now if we think about the free body diagram, so this dot represents the center of mass of the ball. The only force acting on that would be a downwards force, being the weight of the ball. So you can see in that case a very easy free body diagram. There's only one force, so we only need to represent one force on the center of mass of the ball. So a very straightforward diagram there. Second one will be a box resting on the ground, or a box stationary on the ground is another way you could think of it. So again, here's the ground, and here's a box that's sitting on it. Nothing is happening to it, so there's no velocity, there's no acceleration causing it to move in any direction. So fairly straightforward diagram in that case. If we consider the forces that are acting on it, again we have a downwards force being the weight of the box. Now another thing to keep in mind here, when you're looking at the weight of an object, you could actually say that it's the force of the earth pulling on that object. I'm just going to use weight, it just makes it a little bit quicker and easier to label. The other force that you can consider there though is it will have an upwards force, being the force of the ground onto the box. and you'll notice in this diagram that the size of that force, or the size of the force arrow up, is the same as the size of the force arrow of the weight of the box down. We know with Newton's first law, forces acting on an object will be balanced if the object is stationary, and so those two force vectors will be the same length. Last example will be a car parked on a hill. So in this case it's a little bit more complicated. So we've got the hill there, so the car will be positioned on the hill, something like this. And again, because the car isn't moving, we don't have to worry about any acceleration or velocity or any of those sorts of things. The free body diagram here, though, is a little bit more complicated. So as with any object near the Earth's surface, we're going to have the weight of the car pulling it down. In this case, because the surface that the car is sitting on is on an incline, we're now actually going to have the force of the road onto the car will be in that direction. Let me just check that I've got the size of that arrow right. I think I need to just be a little bit shorter. So that will be the force of the road on the car. And because the car's not moving anywhere, there must be a frictional force that's acting up the hill, and that force vector is then the friction between the tyres and the road. So there's a few examples of force body diagrams. Notice here that I'm not actually measuring them out accurately. If you are drawing these by hand, you should really take the time to make sure they are to scale. I've tried to roughly make sure that one's to scale.